Is going to have a look at the calculations that are used to work out the formula of an organic compound using combustion reactions. I put a couple of extra calculations on at the end, which I found when I was going through past papers to source the questions on the combustion calculations. So I'm going to do those as well, because I thought they're just slightly tricky little calculations that don't come up very often, and it's maybe well worth your while being aware of them. So let's get started. So we'll build this up. We'll start with some, hopefully, I think, are fairly straightforward calculations. You may well have forgotten how to do them, so it'll just be a matter of refreshing over them. Again, I think it's probably a good idea, if you're feeling comfortable, just to pause the video, do the question yourself, and then come back and double check it against my answer. Okay, so let's have a look at this one here. Okay, so all I've done here is just take out from the question all the information that it's given us. It's told us we had 10 cc's of the hydrocarbon reacted with 70 cc's of the oxygen, which was in excess, and then it tells us there's 20 cc's of unreacted oxygen at the end. That means that 50 cc's of oxygen have been reacted during the actual reaction. So I can start putting in some ratios here. So what I can say is that 1 mole of the hydrocarbon will react with 5 moles of oxygen, because remember what we're applying here is Avogadro's law, and that 1 mole of any gas under the same conditions has the same volume. So therefore the volume is directly proportional to the number of moles when everything is done under the same conditions, or measured under the same conditions, which is what has happened here. So that tells me that I have a ratio of 3 to the carbon dioxides. Now that tells me therefore that 1 mole of the hydrocarbon can produce 3 moles of carbon dioxide. So the hydrocarbon must have 3 carbons in it. The only place the carbons from the carbon dioxide can come from are the hydrocarbon. So therefore I can get rid of A and B, because they don't have 3 moles of carbon in them. Now I need to know how many moles of water are made, because unless I know how many moles of water are made, I can't work out how many hydrogens there are in my hydrocarbon. Now how do I do that? Well, this is simply a balancing exercise. I have 10 oxygens on the left hand side, and on the right hand side I have 3 times O2, so I have 6 oxygens balanced there. So I'm missing 4 oxygens. The only place I can get my 4 oxygens is from there, and that means that I have 4 HCO, which tells me that 1 mole of my hydrocarbon from over here produces 4 moles of water during complete combustion, and that 4 moles of water contains 8 moles of hydrogen. So 1 mole of the hydrocarbon must contain 8 moles of hydrogen, so the answer is D, C3H8. This one is a very similar question, but it's been presented differently. Okay, and there's a couple of other small things we need to be aware of here. But again, if you fancy doing it, pause the video, have a go at it yourself. Okay, so we've got a tube, and that tube has been filled with 50 cc's of methane and 150 cc's of oxygen. Now the first thing, if you're on the ball here, you will notice is that 50 cc's of methane will only be able to react, because it's a 2-to-1 ratio, with 100 cc's of oxygen. So that tells me at the end of this reaction I'm going to have 50 cubic centimeters of oxygen left over unreacted. The next thing that it tells me is that everything was done at room temperature, so therefore the volume, gaseous volume contribution of the water is going to be 0 cubic centimeters or cc's, because it's done at room temperature, and water is of course a liquid at room temperature, and that water will simply form part of the solution at the bottom. Okay. The next thing that we look at is the amount of carbon dioxide that can be made. Well, if I start up for the 50 of the methane, and the methane is the limiting reactant, which it is, I'm going to make 50 of the carbon dioxide. Okay, it's a 1-to-1 ratio, and we're applying Avogadro's law. So the carbon dioxide has got a volume in there of, what did I say there, 50 cc's, yeah. 50 cubic centimeters of that made. The methane at the end of the reaction is all going to be reacted. It's my limiting reactant, so there's 0 cubic centimeters of that left over. And the water is also 0 cubic centimetres. Now, we haven't talked about the sodium hydroxide. What's the point of the sodium hydroxide? Well, the sodium hydroxide is an alkali, strong alkali. Carbon dioxide is an acidic gas. So the sodium hydroxide will actually react with the carbon dioxide as it's made. Therefore, in actual fact, the volume contribution of the carbon dioxide at the end is 0, because all the carbon dioxide will dissolve and react into the sodium hydroxide solution at the bottom. So therefore, the volume at the end of this experiment is going to be 50 cubic centimetres. So the level of water will be sucked up to level B on the question. Tricky question, okay? Actually made more tricky just by the diagram that was put into it. I think a lot of students, if they had just had that question as words, probably would have solved it much better than the diagram. I think that threw people off a little bit, so just be cautious of that. Okay, let's have a look at this one. It's very similar to the last one, except it doesn't have a diagram, so you probably want to have a pause of the video and have a go at this one, okay? So again, in this one, if we look at it, we had 25 cc's of our hydrocarbons, so we've just put that up there, exploded with 100 cc's of excess oxygen, okay, and we got our carbon dioxide and water. At the end of this reaction, we had remaining 62.5 of the gases after it being cooled back to room temperature. So that's telling us that there's no contribution from the water. There's obviously no contribution from the hydrocarbon because it was the limiting reactant. So the 62.5 is made up of the oxygen and the carbon dioxide. It tells us then that we cooled that solution, or sorry, not cooled it, we added that solution to sodium hydroxide, and the volume reduced to 12.5, so it reduced from 62.5 to 12.5, so minus 50 degree or cubic centimetres. So that's how much carbon dioxide there must be in there. So if we plug all those values in, we also realised that we started off with 100 cc's of oxygen. We're left with 12.5 cc's, so 87.5 cubic centimetres of oxygen must have reacted. So if we put all those ratios in of the volumes, so 25 to 87.5 to 50, then we don't know the water yet, but we can balance it out now. That gives us 2.5 to 8 3/4 to 5, and then whenever we do the waters, we do the waters by working out how many oxygens from here are not balanced out by the 5O2 here, we get a 7.5. Now that's pretty awkward, so the simplest way that I did it here was I divided everything by the 2.5 to bring it down to the sort of the best and most manageable numbers here. So that gave me a 1 there, 3.5 oxygens, 2 carbon dioxides and 3 waters. The carbons and the carbon dioxide had to come from the hydrocarbon. 1 hydrocarbon therefore contains 2 carbons, and the hydrogen's the same, so 1 hydrocarbon therefore contains 6 hydrogens. Okay, so it is C2H6. Answer is C. Okay, next one. This is probably a slightly easier one, to be honest with you. Again, we had a hydrocarbon with oxygen. It tells us that we produced carbon dioxide and we produced water. We started off with 50 cubic centimetres of that. Okay, required exactly 250 of that, so no excess this time. Okay. And after that we produced 150 cubic centimetres of carbon dioxide. Everything was done under the same conditions, so that's just giving us license to use Avogadro's law there, where the number of the volume is directly proportional to the number of moles. Okay, so let's have a look. We can put our numbers in. We have a ratio of 1 to 5 to 3, sorry. Okay, we have, over here we have 10 oxygens, here we have 6 oxygens. I think this is pretty much the same as the one we did earlier, 6 oxygens. So we're missing 4 oxygens, so I need a 4 there. So one hydrocarbon has got 3 carbons in it, and it has 8 hydrogens in it, so the answer has to be B, C3H8. Hopefully you all got that. This is a very similar one. Again, have another go at that one. In fact, I think if I look at it, that's exactly the same question in a different paper. Yeah, with the same numbers, everything, guys. So I don't even need to do that calculation. That answer is B. So that's exactly the same question, different paper, and like same numbers, everything. Okay, let's have a look at this one. A little bit trickier. Again, pause the video, have a go at it if you fancy it. Okay, you should be well capable of doing it by now. Similar to one I did earlier. Okay, so hopefully you had a go at this. It's a trickier, slightly trickier one in the way that it's worded, but the principle behind it is exactly the same. So I'll explain to you here what I've done, if you just follow me through. So we were told we had 20 cc's of the hydrocarbon. We were told nothing about the high oxygen to begin with. We were then told that at the end, the volume of gases after the reaction was 50 cc's lower than at the start. We'll come back to that. We bubbled the gases through sodium hydroxide, and a further contraction of 80 occurred. That tells me that I made 80 cc's of the oxygen. The whole thing was done at 20 degrees Celsius, so the gaseous contribution of the water is 0. Okay, because it's a liquid at that temperature. So let's see how we use this 50 cc's here to help us solve the problem. Well, during the reaction we made 80 of carbon dioxide, we made 0 of water, and the hydrocarbon at the end will have 0 because it's the limiting reactant. Now, the final volume, which was 80 here, was 50 less than the original, so the original volume must have been 130 cc's. But remember, that included 20 cc's of the hydrocarbon. So the original volume, which had to be the gaseous hydrocarbon and the gaseous oxygen, must have been 130 in total, 20 of which is hydrocarbon. So therefore, the amount of oxygen to begin with must have been 110 cubic centimeters. So we can now start to plug in some values, some ratios. So we have hydrocarbon 2, oxygen is 11, carbon dioxide is 8, and the water, we worked that out because we had 22 oxygens on the left hand side. We balanced 16 of them out with the 8 carbon dioxides, and then finally we had 6 oxygens missing, so we had to put a 6 there. That tells us that 2 of the hydrocarbons contained 8 carbons and 12 hydrogens, so a hydrocarbon must have 4 carbons and 6 hydrogens. The answer is C. Okay. This one here, again, similar but a little bit different. The complete combustion of 0.7 decimeters cubed of a gaseous compound at 1 atmosphere of pressure give that amount of carbon dioxide. What is the number of carbons in the molecule? Again, pause the video, have a go at it if you want to. So this time we were working out the number of moles of the gaseous organic compound was 0.7 decimeters cubed. 0.7 decimeters cubed over 24, which is the gas molar volume, the mole of a gas at 20 degrees Celsius and 1 atmosphere of pressure, and that gave us 0.02916. Okay, moles of carbon dioxide we were told in the question. So if I do my 0.12 divided by 0.03, okay, I just 0.03 that, okay, comes out pretty much the same whether I round it up or not, and that gives me an answer of 4. So there must be 4 carbons in every mole of that particular hydrocarbon. Okay, this is one I just kind of threw in a little bit towards because I thought it was a reasonable calculation for you to have a go at. It's not a combustion calculation, so have a go at it, see what you think. It's always good to practice your calculations. Okay, so hopefully you're able to have a go at that. So what I did was work out the RFM of the DDT, which is 354.5. If you make a mistake on that, guys, you're going to be in big trouble in this question, right? So make sure you're calculating your RFM accurately. I worked out that that was 47.4% carbon, and it was 50% of it was chlorine, just by doing a mass of the element over in the compound over the RFM times 100. So therefore I worked out that 0.12 must be equal to 47.4%. So I divided it by 47.4% to essentially work out the mass of what 1% is. I multiplied that by 50 to work out what the mass of 50% would be, made up by the chlorine, and the answer is 0.127. Well done if you got that right. Right, so this one's probably the hardest of all those combustion ones. There's another question like this in the past paper. I did try my hardest to look for it this morning, scoured through about 20 years of past papers, but couldn't locate it. Anyway, we'll do this one, and if the other one pops up, I'll add it to the video later. Right, so let's have a look at this. So we have an organic compound. Okay, it is made up of carbon, hydrogen, and maybe oxygen. We're not quite sure if there is definitely oxygen in it or not. Okay, and when we completely combusted that, we got carbon dioxide, of which we got 8.8 grams of that, and we got 3.6 grams of, sorry, that's a bit, let me get rid of that. We got water, and we got 3.6 grams of water. Now, they were the only products. We've got to work out the empirical formula. So this, again, I pause the video, have a go at this, because this is, without a shadow of a doubt, the trickiest of all of these questions. So, and I'll show you how I would do it. I'm sure those of you who are more mathematically gifted than me could find another approach to it, but this is how I go about it. Okay, so let's have a look. We want to find out how many moles of carbon, hydrogen, and maybe oxygen, but we're not quite sure if the oxygen comes from just the oxygen gas or does it come from the compound itself, but we'll find out. Okay, so over here we've got 8.8 grams of carbon dioxide, so that comes out at 0.2 moles of carbon dioxide. That tells me in here I have 0.2 moles of carbon. Okay, because there's 1 mole of carbon per mole of carbon dioxide. Tells me in total I've got 2.4 grams of carbon dioxide. Over here I have 3.6 divided by 18, so I have again 0.2 moles of water. Now there's 2 moles of hydrogen per mole of water, so if I multiply that by 2, I have 0.4 moles of hydrogen in there. The RFM of hydrogen is 1, of course, so that tells me I've got 0.4 grams of hydrogen in here. So therefore, if I started off with 6 grams of my original compound, 2.4 grams of it was carbon, okay, 0.4 grams of it was hydrogen, so in total, obviously, that's 2.8 grams. So there must be oxygen in the compound, and it must be 6 minus the 2.8 grams, yeah, so we've got, therefore, we must have 3.2 grams of oxygen in there. Okay, if I work out the moles of oxygen, dividing that by 16, that tells me I have 0.2 moles of oxygen. So I now know the moles of everything, so I can easily work out an empirical formula. My carbon, my hydrogen, my oxygen is 0.2 to 0.4 to 0.2. So I'm looking for a formula where the ratio is 1 to 2 to 1, and the answer therefore is C. Well done anybody who got it right. Okay, it is tricky, and there is another one like that out there. They don't ask those very often at all. As I say, there's only that one and one other that I can think of, okay, which I can't find. So right, so those are all the combustion ones done. I've just put these two sort of on the end, just tagged them on, because when I was looking through combustion calculations, I found these and I thought they were sort of a little bit different and well worth having a look at. So we'll have a look at these two. Again, pause the video and have a go at it yourself if you want to, and then I will talk you through it. Okay, so we first of all work out the moles of the magnesium and the moles of the arsenic that's made. We have 3.6 grams of magnesium, which divided by the 24 gives me 0.15 moles of magnesium. My arsenic is 7.5 grams. Okay, and that's divided by 75. The atomic mass of arsenic gives me 0.1 moles of arsenic. So the number of moles of arsenic has to be in a 1-to-1 ratio to the arsenic ions. Okay, it can be anything else. So the number of moles of arsenic ions that I'm starting with is 0.1 to the magnesium 0.15. That gives me a ratio then of magnesium moles to arsenic moles of 0.15 to 0.1, which in whole numbers is 3 to 2. When I carry out oxidation of a magnesium ion, or a magnesium atom, sorry, to a magnesium ion, each magnesium loses 2 electrons. So if the ratio is 3 magnesiums, I must be losing 6 electrons. Remember, in oxidation and reduction, electrons can't be lost or gained, they can only be transferred. So that tells me that the arsenic, therefore, must be gaining those 6 electrons. Okay? So if 2 arsenics are gaining 6 electrons, they must gain 3 electrons each. And if they gain 3 electrons each and they start off with start off with a particular charge, and they go to 0 charge, i.e. the arsenic, well then the N value on the arsenic must be +3. 3. Okay. Right, again, have a look at this one. Another one I just plucked out, might be worth having a look at. Okay, so if we look at this one, very similar to the last one, to be honest with you. We had 2.6 grams of X, which turns out at 0.05 moles of X. Okay, we're given the atomic mass of X further down, so 0.05 moles of X, 4.8 grams of copper was made. Now, the 4.8 grams of copper came from the copper sulfate. Okay, but that has to be in a 1-to-1 ratio. And anyway, so 4.8 grams of copper tells me that I had 0.075 moles of copper to 0.05 moles of X. Now, I multiplied those by 4 to get them into whole numbers, so that tells me 3 moles of copper was made when 2 moles of X reacted. So every time I make 3 moles of copper from copper sulfate, okay, the copper ions and the copper sulfate have to gain 6 electrons. Okay, well, they gain 2 electrons each, but because there's 3 of them, they have to gain 6 electrons in total. That means my 2 X's, okay, have to have lost those 6 electrons between them. So if I have 2 X's losing 6 electrons between the 2 of them, the X's must end up as a 3+ ion, making our answer very similar to the last question, as I said, C. Hope those help, guys, for some of the slightly more off-centre kind of calculations that come up. They don't come up very often, but when they do, students do struggle with them a bit, so it's a good idea that you're exposed to them and know how to do them.